Okay. All right. I think we are live on YouTube. Sorry about that. Thank you, Andrew, for letting me know. All right. So if you're watching this later on YouTube, sorry, started the stream a little bit late. But all we've gone over is the transient conduction heat diffusion equation for a long cylinder. A long cylinder is one in which the length is greater than 10 diameters. Sometimes we refer to as an infinitely long cylinder. All right. So we've taken our heat diffusion equation, applied an initial condition, first boundary condition. Second boundary condition is the temperature at R naught minus T infinity. We will define a non-dimensionalized temperature gradient, or not temperature gradient, but a non-dimensionalized temperature. And this is going to look really, really similar to the non-dimensionalized temperature that we had with our Cartesian coordinates. So this is, and actually I'm gonna pull it up right here. Here we go. So we're going to be looking in this whole region is what we're going to be looking at. So here's our non-dimensionalized temperature. There we go. So T at some particular location and time, right? Looks really a lot like that. Minus T infinity over T initial minus T infinity. So really almost the same as that non-dimensionalized temperature that we had before. So again, T at R, T minus T infinity over T initial minus T infinity. Supposedly, I feel like that's all kinds of butchered. It's okay. Supposedly makes the math easier. But you know what? Doesn't matter. Because somebody else solved it for us. Yay! All right. So it's this guy right here. And you'll notice that unlike this one, it doesn't have a little summation. It doesn't indicate that it's a series solution, but it is. It is a series solution. But I just wrote it with the one-term solution because in this class, we're only going to evaluate that series solution using just one term. Again, just like for Cartesian coordinates, that one-term solution is valid if your Fourier number is greater than 0.2. Essentially, you've gotten past that initial, like, bam, we turned on convection, right? We've exposed this thing to some convective environment, and it's just during that first little bit. It's not during that portion, right? So if our Fourier number is greater than 0.2, one term solution is fine. All right, so let's look. Oh, go ahead. I'm sorry.
Sorry, I was just confused why the Cartesian one, why that has the summation symbol, but the other one doesn't. If it seems like, and maybe I'm just misinterpreting what you're saying, that in both cases, like basically for everything we're going to see in this class, we're only going to be doing it to one.
Yes.
Oh, okay.
So
I thought I
there is
misunderstood.
absolutely no rhyme or reason why I chose to leave the summation on that one and not the other guy. There is a summation, but with both of those, we're always going to be just using one term.
Awesome. Thank
Yeah.
you.
Yeah. Okay. So I've got a C1 in there. I've got an eta. And you'll notice like, well, this and this, right? There's some similarities there. This looks a lot like this guy, and it is, although our zeta value is going to be a little bit different. Yeah, so the exponential portion of that solution is dealing with the time component. And then the next one, whereas in the Cartesian coordinates, that was, a cosine to describe the position portion of it. This is what's called a Bessel function. I don't know, you may or may not remember it from calculus. And somewhere in your book, there is probably there's probably the actual equation that goes with that Bessel function so that you know, well, I input this, and based on that, then I'm going to get this output, and you would calculate it. You don't have to do any of that because guess what? We have a table. So let's go look at it real quick. Yeah. So just scroll down. It's table B4, but it's just on the next page of that equation sheet. And all you're going to do is look up, what you're inputting, and then you'll get the output, right? So you've got this one with a little subscript 0, this one with a little subscript 1. Just make sure you're looking at the correct one. So in that equation for theta star, it's going to be this column right here. Okay. Anything else I want to say about it? Not really. I guess the only other thing I will say is that make sure, and I realize that something kind of screwy happened with my PDF here because it should say infinite. Apparently one of those letters got dropped. But yeah, make sure that you're reading not on the plain wall, but you're looking at the infinite cylinder. We're not going to do nothing with spheres. We're not going to do anything with that. So you're going to look at your Biot number and then just read off the correct zeta or C1. You may remember with the lumped capacitance model, we were specific on how we were going to define that Biot number because that was dependent on the characteristic length, right? Your Biot number is HLC over K. Sorry, just like blanked for a second. And LC, we said, okay, well, it could be like for a cylinder, sometimes it's R naught over 2, sometimes it's R naught, right? When you calculate your Biot number to see if the lumped capacitance method is valid, you wanted to be conservative, so you would use R naught for your LC. And then when you actually used it, that LC, which is defined as volume over area, then you would use the R naught over 2. Don't even have to worry about that. It's R naught. And so that's what you're going to use here. So if you've already decided to use R naught because you want to be conservative in deciding whether or not the lumped capacitance method is valid, you are already one step ahead of the game because that's what you're supposed to use to calculate the Biot number for this table. And if you forget, it's actually on here. So you don't even have to remember. It's right there. So your Biot number is HR naught over K for, again, infinite cylinder. It just means it's a long cylinder. That's all. Okay. Alrighty. There's also this equation over here. So there's Q over Q naught. The last problem we do today, we're going to use this equation. We'll get a chance to practice using this. This is going to be in joules, right? So this is Q is it's the amount of heat that's transferred over a certain time period, and that the amount of that time period that you're accounting for is going to be accounted for with this theta star. It'll become a little bit more obvious when we actually use it. And this Q naught is the maximum amount of heat that could be transferred. So we could just call it Q max. But that would be the maximum amount of heat transfer that occurs as that cylinder comes into thermal equilibrium with its environment. That's all. All right, but again, we'll have a chance to sort of practice using that equation. So I think we're ready to move on. Let's move on to a problem. And just like last night, we'll practice. We'll see if, oh, that's not a, I'm sorry. We will see if the Heisler charts make our life easier. I don't know. Sometimes they make it easier. Sometimes it's a little bit, it's confusing, but all right. And I am going to not start with problem 13. I'm going to skip to problem 14 and then I'm going to come back because I feel like problem 13 is a little bit more difficult than 14. So let's start with a little bit easier one. All right. So we have a long cylinder, 30 millimeters in diameter. You start writing stuff here. All right. So there we are. There we are. So we have a diameter. I am just going to define a radius. So R naught is the outer radius. So it's 15 millimeters. So 0.015 meters. Perfect. Okay, hold on just a second. Hold on just a second. Sure, we're good here. Lord have mercy. Okay, sorry. I'm yelling at my son. He's supposed to hop. He has a Mandarin lesson at 5 o'clock, and it's the same time every time. Anyway, 5:17, not on yet. Anyway, I digress. All right, so R naught is 0.015 meters. I can't understand Mandarin. I've got ni hao, and that's about it. Yeah. So initially at a uniform temperature of T1 is, or T initial, I'm sorry, T initial, dang it. I want it to look pretty. T initial, 1000 Kelvin, is suddenly quenched in a large constant surface temperature oil bath. So let's make this blue. So our T infinity is 350 Kelvin. And then we've got some properties. I'm not going to rewrite the properties. I'll just kind of highlight them because, maybe they'll be useful at some point. And then the convection coefficient is 50 watts per meter squared Kelvin. Perfect. And we want to find the time required for the surface of the cylinder to reach 500 Kelvin. So, okay. So we want the time when the surface, so at R naught and some particular time, is equal to 500 Kelvin. Perfect. All righty. And I'll throw an assumption on here. There we go. So they do say that it is a long cylinder. So I'm going to go ahead and throw on there that it's, one-dimensional heat transfer. And I'll double check and, check by Biot number and see if it's less than 0.1. So if it is less than 0.1, then it gets a lot easier. Or my calculations get a little bit easier. And if that's the case, I'll just mark out the 1D, but I don't know. Probably not. I suspect not. Okay, we'll do pink. How's that? A little bit obnoxious, but that's okay. All right, so we're going to calculate our Biot number. Perfect. All right. So we have a Biot number. So it's H R naught over K. All right, so I've got 50 watts per meter squared Kelvin. R naught, 0.015 meters. Divided by K, which is one of those things I didn't write down, but I highlighted, so 1.7. So 1.7 watts per meter Kelvin. And I have a value of 0.441. Aw, buoy. So, Can't use the lumped capacitance method, but that's okay because we have a one-term solution. So assuming that that Fourier number is greater than 0.2, we're going to use that one-term solution. All right, perfect. So I'm going to copy it straight off of my equation sheet. So I have a theta star, which is t at whatever position and time that I am interested in. So I'm interested in position at r naught at the surface, and I'm interested in a particular time t minus t infinity, and then I've got t initial minus t infinity. Perfect. All right, and I know that this is equal to c1 e to the negative zeta 1 squared times our Fourier number. And then I've got our Bessel function here. And the thing that I'm going to input, I have a zeta 1 value and then something called r star. And that's defined really similarly as to how we defined x star. So whereas x star was x over L, well, r star is just r over L. Or not r over L, r over r naught. I'm sorry. Okay. So in this case, because we're talking about r naught, well, this is just 1 in this case, right? This is 1. Okay. Okay. So let's go ahead and we'll need to get our C1 and our zeta. So those guys we're going to get from, I think it was table 5.1. So let's go look. 5.1. All right, I started scrolling down before, didn't I? Ah, perfect. So that's this guy right here. All right. Delete that guy. All right, so our Biot number was 0.441. So that's going to be between this guy and this guy. And then for my infinite cylinder, so that would put my zeta between those guys and my C1 between those guys. So a question was asked, can you explain the R star again? Will it always be 1 or 0 in this class? Yeah, I mean, I can't think of any other like things that like any. The dog's back. Okay, put her down. um, I can't think of it. Yeah, it's either going to be R or R star. Yeah. Okay. So let's see what we've got. Okay, so we have theta 1 and R star. I mean, technically it could be, I mean, I'm sorry, you said R star and then I was like, I had it in my head. Okay. So I've got a zeta 1 value of, I don't know, point. She doesn't want to either. We're going to run out of animals at some point. So 0.8882 and a C1 of 1.1019. All right, so we get those from our table 5.1. All right, so let's see what else we got. Okay, so now I'm just going to plug in numbers, I guess, because I think I have everything, don't I? Yeah, I got everything. So I've got 500 Kelvin. Got my 500 Kelvin minus our T infinity, which was 350 over T initial. Oh my God. Okay. Okay, they're done. Please take the chicken away. Okay, that's enough. All right, y'all go. Y'all go.
Tell your son thank you so much. Made my day.
I will. Okay, that's enough. Y'all go. Stop it, stop it, stop it, stop. Go, 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 go. Go away. Okay. T initial, 1000 Kelvin. They are so pleased with themselves. All right, so this ends up being 0.231. Oh my gosh. All right, 0.231. And then I've got the other guys. So this is 1.1019, and then I have e to the negative, the zeta, so 0.8882 squared times our Fourier number, times that Bessel function. Perfect. So this one, so it's going to be zeta times 1, so 0.8882. Okay, perfect. Alrighty. What is Joe? We have a cat, Joey. I don't know. Joey made an appearance yet. He'll make an appearance at some point. Maybe like next week or something. All right, so let's go look up our Bessel function here.
I think they mean the J sub 0.
Okay, I'm sorry, I was still on thinking about animals. Yeah, so this is a Bessel function. Yeah. I like Joe though. Yeah, yeah. I think Joe sounds better than a Bessel function. Yeah. But I can look that stuff up. So this is going to be in table B4. So let's see. If I'm putting in 0.8882, going to be between this guy and this guy. So that means that my output is going to be between this guy and this guy. And so I end up calculating a value of, you do have to interpolate. I've got 0.8121. No, that's enough. No more animals. It's okay. Okay, 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 go away. Done with the animals. Go away, go away, go away, go away. All right, so this ends up being 0.8121, 0.8121. Okay, and so now I'm going to solve for my Fourier number. All right, so I end up getting a Fourier number of 1.72. 1.72, and then I know that that's equal to my thermal diffusivity times the time that I'm interested in, right, over my LC squared. In this case, my LC is the R naught. So R naught squared. I don't think at this point they had actually, I don't think I actually had the thermal diffusivity. I don't think that was something that was given to me. Let's just double check real quick. Yeah. So it looks like they gave me the K, they gave me the C, they gave me the rho, but they didn't give you thermal diffusivity. So we'll go ahead and calculate that. All right. So our thermal diffusivity is K over rho Cp, or just C. I guess that's how we've written it. So I end up getting a value. I don't know what I've got, but whatever this 1.7 times 1.7 divided by 1600 times 400, and this is going to be in terms of meters squared per second. So whatever that guy is what I'm going to plug into that Fourier number. All right, so let's make sure that we can see that. All right. And so I end up getting a value.
Oh. J naught turn times zeta all equal to the 0.8121, or is that just the J naught value?
So the J naught is a function. And that table B4,
gotcha.
Yeah. So you can look up, like, I put this thing in and it spits this thing out. Yeah. So I end up getting, for the time, I had it in green before, so I should keep doing that. That was 145 seconds. Perfect. Perfect. Awesome. All right. So I think before we go on to back to problem 13, let's see if we could actually solve this using the Heisler charts, just in case somebody likes them. I know everybody seemed to not particularly like them the last time,
that
but
JO value that was in the table.
yes. So it's a function. You put this value in, it spits this value out. And you just have to say, well, for this given input, what's it gonna spit out? So we were putting in 0.8889, and it was gonna spit out something between those two. Okay. So I'm gonna go look at my Heisler charts, and it's gonna be on the very last page. Oh, let's see, just okay, perfect. All right, so it's the very last page. That's the one with the cylindrical coordinates. And so the ones that we'll use are just this one, and this one. And that last one at the very bottom left-hand corner we'll use on the very last problem. Okay, so let's kind of take a beat and think about what we were asked for before. So we were asked, we wanted to find we wanted to find the time when the temperature at R naught in that particular time was equal to 500 Kelvin. So clearly, if I look at this first chart, the first Heisler chart, so 5S4, what I'm going to be needing to find is I need my Fourier number. So I definitely am going to at some point need this chart. And well, let's get the inverse Biot number. So our inverse Biot number, let me go ahead and things pulled up here. All right, so my Biot number was 0.441. So 1 over that. So 1 over 0.441 was going to be 2.27. All right, so at least I have that. Is it R naught in the last equation? Let's see. Yes, it's R naught right here. That's an R naught because that's the characteristic length. Welcome. All right, so I need that Fourier number. So let's see if I have enough information to maybe get what's on the y-axis here. So I have a T naught. Yeah, so if I look at what's on the axis here, on the y-axis, I've got this, I've got this, I've got this, but that T naught is the temperature at the center, so I don't have that. However, maybe I can use the Heisler chart that's over here. Maybe. I don't know. Let's see. Should I bring Hugh over here? Hopefully my head's not too much in the way. All right, so I've got my inverse Biot number. So my inverse Biot number was 2.27. I am interested in the temperature on the surface. So that one right at R equals, or at R over R naught is equal to 1, right? So my Biot number, if my inverse Biot number is 2.27, well, let me see something real quick about where am I going between those. Oh. this a little bit like that. All right, so this is 2, that's 3. Right there in the middle is 2.45, so it's like a little bit to the left of this. Gosh. I wish I had the ability to draw a straight line, but apparently I do not. But it's going to be right there. And then right where it hits that guy, I'm going to bring it all the way over so it looks like, I don't know, maybe really close. Let's call this about 0.83 roundabout. Okay. So how is that going to help me? Well, I know theta over theta naught. Now I know theta over theta naught. I know that's equal to 0.83. And so now that looks like I could probably just solve for T naught at this particular time, right? So that's going to be, well, the T, this guy, is the temperature at the surface. So this is going to be 500 Kelvin minus T infinity, 350, over T initial, 1,000, oops, not 100, 1,000, oh, I'm sorry, oops, not initial, lies. T at the center when the surface is 500 Kelvin minus our T infinity. There we go. And so I should be able to solve for that T naught. Let's see what I've got. So I have 150 divided by 0.83 plus 350. Oops. So I end up getting 530 Kelvin. So hopefully we're okay up to that point. And I needed that value because I needed that value for that first Heisler chart, which we're going to go over to right now to pull off the Fourier number. So now that I know that, well, now I've got enough information to calculate this guy. All right. So I've got a theta naught star. So this is going to be apparently 530 Kelvin, right? What I got right here, 530 Kelvin minus T infinity over T initial minus T infinity, right? So let's see what that ends up being. So I've got 0.28. So about 0.28. All right. All right, so that theta star naught, 0.28, it looks like I probably need to go up here. So 0.28, and my inverse Biot number was the 2.27. Yeah, 2.27. All right, and then this is 0.28. So 0.28. All right, so let's see. Donate that. All right, so it looks like, yeah, kind of halfway between this guy and this guy. That right there would be about 0.25, so it's a little above it. So somewhere maybe on that line. And then my inverse Biot number, 2.27, so looks like, I don't know, maybe about right there. So I've got, that looks like about a Fourier number of round about 1.8. When we calculated what that was, we got a Fourier number of 1.72. So that's, I mean, it's pretty close, I guess. Yeah. I don't know. Sometimes it saves you time, sometimes it doesn't. Anybody got questions about the Heisler charts or?
Could we go back to the solution for this problem? I didn't get the.
Yes, absolutely. Yes. Okay. Okay. All right, so let's go on to problem 13 because that one was maybe a little bit more difficult. It's actually a little bit more difficult by hand and then surprisingly easy with the Heisler charts, believe it or not. So, but we'll see. All right, so again, we have a long rod initially. Initially it is, and it's 60 millimeters, oops, ugly, 60 millimeters in diameter. So our R naught is 30 millimeters, so 0.03 meters. And then I'm going to be lazy and just highlight the properties so I don't have to write them again. Okay. And then it's at a uniform temperature, but I don't know what the uniform temperature is, but some uniform temperature, question mark. And it's heated in a forced convection furnace maintained at T infinity 750 Kelvin. Convection coefficient is estimated to be 1,000 and it's watts per meter squared Kelvin. And we want to find the center line temperature. So the temperature at R equals 0, which is going to be at some time. I don't know what it is, but we want to find the center line temperature when the temperature at the surface, and that same time, of course, is equal to 550 Kelvin. All right, so I'm going to go ahead. I noticed that it says it's a long rod. Great, so I'm going to assume if there are spatial effects, it's just going to be in the radial direction. But of course, I'm going to figure things out pretty quickly, see if we have to consider spatial effects by calculating that Biot number. So step number 1, get our Biot number. So our Biot number is equal to H R naught over K. So this is 1,000 watts per meter squared Kelvin. Our R naught is 0.03 meters. And then our K value, oh, it's written up there, 50 watts per meter Kelvin. It's in the problem statement. All right, see what I've got. I end up getting 0.6. Perfect. So yeah, we have to consider spatial effects, no problem. Again, let's go ahead and, assuming that Fourier number is greater than 0.2, we're going to use the one-term solution because it's really the only one that we have. Or at least the only one that we have on that equation sheet. All right, so that's fine. So we have I got a theta star. And I'm wanting to know the temperature at the center line. So let's define that theta star. And I'm going to put a little naught there because if I'm defining things at the center line, that's what I'm going to give it a special name, right? So this particular guy, that temperature minus our T infinity over T initial minus T infinity. Okay. Well, so far there's some stuff I don't know, right? I've got two unknown temperatures there. I don't know this guy. That's what I'm trying to solve for. And I don't know this guy. Of course, I know the T infinity, but that's kind of it there. Okay. So that's equal to, I have a C1 e to the negative zeta 1 squared times our Fourier number. Okay. And then I've got the spatial dependence, which is our Bessel function, otherwise known as Joe. And our input is going to be zeta 1 times our R star. But this one is really easy because that R star here, well, we're looking at things at the center. So this is R over R naught. And again, since we're looking at the center, is just 0, right? Because R is equal to 0 at the center. And so if we input a 0, what we'll find, and let's go verify that really quick. If I input that, you can see input a 0, it's going to spit out a 1. So that becomes really simple very quickly, doesn't it? So, okay. So that's equal to 1. And again, we got this in table B4.
Why is R over R 0 in this problem and not in the other problem?
Because in the other problem, we were looking at the surface. So here we're looking at R equals 0, but in the other problem, we were looking at the temperature at R, that instead of a 0 being there, it was defined at R naught. So you see, like, just going back just to the basic equation on your equation sheet, it just depends on, where is it? Where are you defining that R? See what I'm saying? So here's your theta star, here's your theta star, and you're defining that based on a dimensionless temperature defined at a given R, and that's going to depend, or that's going to affect what that R star is, or where you evaluate that R star.
Can you quickly go over the difference between the last problem and the R? I know you just said it, but I kind of didn't.
All right, so I'm gonna go back to problem 14. So with problem 14, we were interested in the temperature at the surface at R naught. And so when we filled in the information here, we were filling in the information for R naught. And so that R star is going to be defined at R naught, right? Because now we're defining that particular R as R naught. So that was problem 14, but the problem that we're working right now, we're not interested in the surface. We are interested, or at this particular junction, we are defining things for R equals 0. So R equals 0. So now R star is, well, it's equal to 0 over R star, as opposed to 0 over R naught, as opposed to R naught over R naught.
Thank you.
Yeah. All right. So perfect, I guess. Kind of perfect. Maybe not really. I guess I can look up these guys. I can look up my C1 and my zeta 1 in table 5.1. So 0.6 is a nice even number, so we will get a little bit of relief that way because we don't actually have to interpolate anything this time, thank goodness, because it's right on there. So at a Beat number of 0.6, we can just pull off the zeta 1 and the C1 value. All right. So 1345. All right. This is 1.1345. And then it's e to the negative, what was zeta again? Ah, perfect. 1.0184 squared times our Fourier number. Perfect. Times 1, right? Because that Bessel function, we input 0, we're going to get a 1. And all of this is equal to t at, right, the same thing. I'm just kind of bringing things down. Perfect. And this is equal to theta naught start. So again, this is all being defined at r equals 0. But now we're going to do the same thing. We're going to define that theta star at r naught, because I've got some information about, right, I need to relate these two things here. Right. So at r naught, I have a theta star. So he's going to be equal to, all right, so it's the temperature at whatever position and time I'm looking at. So this is r naught T minus T infinity over T initial minus T infinity equals C1 e to the negative zeta 1 squared times our Fourier number. So that's that one. And then we've got our Bessel function. We're inputting zeta 1 times our r star. But this time, because we're looking at r naught and we're defining things at r naught, this becomes, so it's defined as r over r naught, but we are looking at r naught over r naught, so it's just 1. And so this now is, what we're inputting is 1 times that zeta value, which is still, it's still 1.0184, right? That's where, and we got those values, that C1 and the zeta 1 from our table 5.1. Okay. All right. So if I look at this guy, what I'll notice, and by the way, these are this time right here, sorry, it's pretty ugly. This time right here is the same time as what we were defining for R at 0, right? It's the same one. So let me kind of highlight some of the similarities between these two guys. So looking up here, I can see, okay, I've got a C1 here. I have a C1 here, right? That's that one. That's the C1. And I've got this guy. And it's the same guy here. Right, same Fourier number because it's the same time. Oops, stop it. And that's the same thing right here. Right? And so basically this whole thing here is that, right? So what I'm going to do is I'm going to rewrite this. I'm going to rewrite it as, okay, well, this is theta star is equal to T R naught T minus T infinity over T initial minus T infinity. And because that this whole thing right there is equal to this, that's what I'm going to write. This is equal to theta star naught, but oops, I'm sorry. I'm so sorry. But I still have this part too that I've got to put in there. So this is going to be times J times my Bessel function, and then I'm inputting that 1.0184. All right. So now, almost there. In fact, I think what I'm going to do is I don't really need him to be here. I'm going to erase him. But what I am going to do is I'm going to rewrite some stuff. I'm going to say, okay, still, this is R naught at some time. Minus T infinity, okay, over T initial, minus T infinity. And that's equal to theta star naught, which is equal to T at R0, R is equal to 0 at that same time, minus T infinity over T initial minus T infinity. And then we've got our Bessel function where we're inputting 1.0184. All right. And so what we can see is that it doesn't matter that I never knew the T initial from the get-go, because it's going to cancel out on both sides. I can look up this guy. So I'm going to look him up in table B4. So let's see what he is. All right. All right, so table B4, so we're inputting 1.184. So he's going to be 1.184. It's going to be between this guy. I'm sorry, 1.184. It's going to be between this guy and this guy. So I end up getting 0.75. Wait a minute.
We can't see what you're highlighting if you were highlighting.
Oh, it's too light. Well, good, because I highlighted the wrong thing, so it works out really well for everybody. Yeah, so 1.0184, so it's going to be, can you see that?
Yes.
Okay. Yeah. So I end up getting 0.7568. That looks okay. So 0.7568. $0.75. All right. And so now I just need to solve for this guy. The temperature at R equals 0. And this particular time at which the surface temperature was 500 Kelvin. And I've got everything, right? I've got T infinity. This guy is 500 Kelvin. So I end up getting 486 Kelvin. All right. Bring that over there.
Can you address again between like the second to last line and the third to last line, what ended up happening with the that little box that you highlighted around? I think my dog must have distracted me. Like
Okay, so let me. I'll walk. Okay, so this whole term right here in that equation that we were defining for theta star at R equals R naught, that's equivalent to this whole thing right here. That's equivalent to this. That's equivalent to, right, because this last one right here, that ended up being just 1. So that whole box that I've highlighted in kind of orangish right here is equal to theta star naught. And it is because it's only dependent, that part is only dependent on the time. And we are looking at the time when the center is at a particular, we're looking at the temperature at the center at the same time that this guy is the surface temperature is 550 Kelvin. So the time is the same when I'm defining things at R equals 0 and R equals R naught.
Got it. Okay,
yeah.
Thank you.
Yeah. All right. So let's go ahead. Let's see if we can do it with the Heisler charts, because this one, it actually did make it a little easier, I'll tell you. Let's see. All right. So number 1, let's, oops, clean it up a bit. Okay. So the equation, or the chart that I'm going to be using, is this one over here that my head is in the way of. You know what I'm going to do? I'm going to move myself over here. That way I can make him bigger. Okay. So this is our inverse Biot number. So our Biot number, looking at what we have over here. So this guy is my temperature that I know, the temperature at the surface. Okay. So let's write this, plug this stuff in. So this is going to be, actually, I can't write like that. My mouse is going to drive me crazy. So it's theta over theta naught. So it's the temperature at the surface, which was 550, right? Sorry. Yeah. 550 Kelvin minus T infinity, 750 Kelvin, minus the temperature at R equals 0 at the same time that the surface temperature is 550 Kelvin, minus the T infinity. So if I can pull that value off, then I'll be good. And this temperature right, oops, I'm sorry. This temperature right here, we're defining that at the surface. So the line that I'm going to be looking at, right, R over R naught, is going to be R naught over R naught, which is 1. So let's see if I can do it. So my inverse Biot number is 1.67. And if I look, make this a little bit smaller. So it's going to be between 1 and 2. Halfway in between is going to be the square root of 1 times 2, which is 1.4. So this is actually going to be a little bit like this. It's going to be a little bit to the, and I know there's going to be some variability because we're reading it off a chart. That's why I say make sure make sure that you a little bit actually over here. I don't know, that's pretty close to 0.8, maybe a little bit less. So, well, let's, maybe we call this, I don't know, 0.78. Well, we could solve for a T naught. So, and remember this, you know, calculating it by hand was a little bit more time consuming, to tell you the truth. So I've got 550 minus 750 divided by 0.78 plus 750. So I end up getting a T naught of 493. That would have been my answer. If I had thrown stuff in the, or when I threw stuff in my equation, I ended up getting 486. I don't know, that's pretty good, pretty close, right? So, but just make sure that if you're going to use these charts, make sure that you draw it and then scan it in with your work. All right, anybody got any questions? Okay.
Mind showing the analytical one more time?
Absolutely, yes. So I tell you what I'm going to do. Well, let me move my base back over here. Move that. Okay. How's that? And then maybe you can take a...
Perfect.
Yeah.
Yeah, I got a screenshot. Thank you.
Okie dokie. All right, so let's go to the next problem. Problem 15. Okay. Long cylindrical stainless steel rods. Perfect. Super exciting. Here's my K. Here's my thermal diffusivity. I don't want to really write it down again. There we go. But here we go. So here's this guy. Here's that guy. So yeah, I got some English units, but it's not too bad. Really, I think the only thing I'm going to end up having to like reconcile is probably just the inches, but we'll see. So they give me the diameter. I'm going to write 2 inches. Well, good. See the charts. Some people like the charts, so yeah, there we go. We'll continue using them, but you don't have to if you don't want to. All right. So they are heat treated by drawing them at a velocity of 10 meters per minute through a 30-foot long oven maintained at 1700 degrees Fahrenheit. So draw him definitely in red. Heat transfer coefficient. All right, holy units, Batman. BTU per hour foot squared degrees Fahrenheit. There we go. And then they give us, so they've given us that they're pulling it through this thing 10 feet per minute. The oven is 30 feet long. So they're going to be asking, they ask if the rods enter at an initial temperature of 85 degrees Fahrenheit. We want to find the temperature when they leave. So I actually know how long it's been in there because, and I'm just going to put it right here. I know probably shouldn't go in my givens, but I think it might be okay. So it's 10 feet per minute. It's 30 feet long. 10 feet per minute. So it looks like 3 minutes. Okay. So we want to find the centerline temperature at that point. So perfect. Easy peasy. So we want to find the temperature at R equals 0 and 3 minutes. Perfect. And I don't really know what I need to assume, but here we go. So I'll go ahead, I might want to go ahead and put, one dimensional in the radial direction, but if I find a Biot number less than 0.1, then of course I'll cross that out. So, but that is definitely step number 1. Get the Biot number. Right. So our Biot number is HR naught over K. So I end up getting a value of something. Yeah, so there's some units there, but it's really just the feet and the inches that need to be reconciled. So, but I've got 0.4307 my Biot number. So no, I can't use the lumped capacitance method, but that's fine. So we will go ahead and use that one-term solution. So one-term solution. And we could, if we wanted to, we could check to see what the Fourier number is. It's a good idea, but I will tell you, even if it's kind of close to that 0.2 on the test in this class, go ahead and say that one term is going to be fine. But I have a feeling I'm going to need my Fourier number anyway, so might as well just calculate it. So I've got my thermal diffusivity times the time, which was that 3 minutes. Clearly, I'm going to have to put that in seconds, so 180 seconds. Thermal diffusivity times the time divided by R naught squared. And I believe they did. Yep, they gave me the thermal diffusivity. It's that 0.91 number up there. Got a feet squared. So I just need to make sure that the feet and the inches are reconciled. But other than that, it's not too bad. So I've got 0.243. Perfect. Oh, and I guess I need to write down that one-term solution, don't I? So, all right, so I want to know the temperature right at R equals 0. All right, so I'm going to be looking for T at R equals 0 and 3 minutes minus T infinity, which I've got. I won't write numbers yet. And then over T initial minus T infinity. And I've got those things too, got T initial. And this is equal to C1 e to the negative zeta 1 squared times our Fourier number, which I already calculated. That's nice. Times, then we've got the spatial dependence portion of it. So Bessel function, and we are inputting zeta 1 and R star. But this will be really easy because I am looking at R equals 0, right? And so that R star will be 0 over R naught, or just 0. So if we put in 0, it's going to spit out 1, and we can verify that by looking at table B4. Okay. I guess the only other thing to do, so like if I look at like what I know this guy, this guy, this guy, and I have pretty much, I'll be able to find everything, except that, and then I have one equation and one unknown. So I do need to get my C1 and my zeta, and so that's going to be table A1, or not A1, A5, right? A5 or A4. I can't remember. A4 or A5. Maybe it's A5. But I got a C1 value 5.1. Okay, there we go. There was a 5 in there. I mean, I should totally get credit for that. Maybe I should stop pretending. Okay, table 5.1. Yes, thank you, Matt. All right, so I have a Biot number of 0.43, so it's going to be between this guy and this guy. So there we go. Get rid of that guy and that guy. Okay. So it looks like, yeah, zeta is going to be between 0.85, 0.94. I've got, let's see, 0.8784. That seems okay. And a C1 of 1.0995. That looks okay too. So let's write that. So again, table 5.1. I got a C1 and a zeta 1. Then my C1, again, 1.0995, and my zeta 0.8784. Okay. Perfect. All right. Okay. So I've got enough information I can plug in and get my, get that value. So my temperature at 0 and my 3 minutes, R equals 0 and 3 minutes. I end up getting a value of 228 degrees Fahrenheit. And that's my answer. So we will go ahead, let's do the same thing. Yeah, let's kind of, okay. So let's go ahead and solve it looking at the Heisler charts. Yeah, see what we got there. Oh, again, so that's going to be page 41. All right. All right. So we are looking at an inverse Biot number. Let's at least write that down. So we know our Fourier number, right? Maybe this will be useful. So we know our Fourier number. Our Fourier number is 0.243. Still above 0.2, barely. And then what else did I know? So I was wanting to know the midline temperature, at R naught. Yeah, so I guess, and then this guy, our inverse Biot number was 1 over 0.43, 0.4307, so 2.232. There we go. Okay, 2.32. Yeah. So I think again I'm going to need to go to this one down here. So 0.243. I need to go to this little cutout up here, 0.243. So Fourier number 0.243. I don't know, about 2.4, yeah, probably about there. 2.43. And then our inverse Biot number, of course, is 2.32. So about right there. Maybe put it like right there. There we go. And so what that gives us, I don't know, pretty close. So, I don't know, 0.1918, something like that. This is equal to T at R equals 0. Oops, I'm sorry. Minus T in infinity over T initial minus T infinity. And you could solve for a T naught. In fact, let's do that. Make sure that we haven't done anything squirrely. So 0.19 times our T initial, 85 minus 1700. Plus the 1700. Oh, that seems not right. Plug something in. Done something. I did so. Oh. Can anybody see what I did? What was my Fourier number?
I was gonna ask that. I thought it was 0.243, not
It,
2.43.
It is. I was like, why is my math not working out correctly? Well, okay, fine. Thank you. That's not, something's wrong. All right, so 0.243. Okay, so like right here, 0.243. There we go. So, oh my goodness. So I think I kind of followed the line up here. I'm like, I don't know, I might say like 0.9. I might say 0.9. So not the 0.19. Let's get rid of this. Get rid of that guy. So if I used 0.9, I think that improves things dramatically. Much better. I would have calculated a T naught of 247 degrees Fahrenheit. And if we did it analytically, we got 228, so pretty close. Pretty close. All right. One more. One more. You want me to go back to that? Maybe I'll go back to the analytic one. If you want to take another picture, you can. Kind of zoom out if you want to take a screenshot. And then we'll do the very last one. Okay. The very last one. So we have a long 35 centimeter diameter shaft made of stainless steel. So we've got some property. Oops, I'm sorry. We got some properties here. There we go. I don't want to rewrite them. That seems like a waste of time. But I will write my little diagram here. So there we go. I don't know why putting the same cylinder doesn't seem like a waste of time, but it doesn't. All right, so what is it? 17.5? Yes, 17.5 centimeters. So 0.175 meters. Comes out at an initial temperature. So it says comes out of the oven at a uniform temperature of 400. So that right there is the initial temperature. That's 400 degrees Celsius. Then it's allowed to cool slowly. So in an environment that is at 150 degrees Celsius. Average heat convection heat transfer coefficient of 60 watts per meter squared Kelvin. All right, and then we want to find the temperature at the center of the shaft 20 minutes after the start. So it looks like we know this guy. So I probably want to put him in terms of seconds. So we got 20 minutes and 60. Okay. All right, so I'm sorry, not 120, 1200 seconds. Yeah. All right, and then we want to find the temperature at the center at that point, and then we also want to find the heat transfer per unit length. So let's go ahead and get that guy. All right, so for part A, we are looking for the temperature at 0 and 1200 seconds. And then for B, I'm looking for the heat transfer per unit length, so Q over L. All right, I'm going to assume one-dimensional heat transfer. And then if my Biot number ends up being, less than 0.1, then so be it. So I do need to calculate that Biot number. So H times the characteristic length, which is R naught, over.
Oh, you're getting lazy.
I was getting lazy. I'm so sorry.
Solution.
I know. I'm sorry. How much work was it to write out solution? Apparently too much. But I've got 0.705 for my Biot number. 0.705. Perfect. So I can't use lumped capacitance method, but I can use my one-term solution, hopefully. And I actually have enough information to calculate that Fourier number. So my Fourier number is my thermal diffusivity times the time I'm looking at over R naught squared, or the characteristic length squared, so 0.175 meters. And I actually end up getting a value of 0.1548. And since I've sort of been harping on that Fourier number having to be greater than 0.2, this is the place where we're going to say, well, it's close enough. And you can use that argument too, that it's close enough. And on a test, it's close enough. So one term solution. All right, so my theta naught star. All right, so this is going to be the temperature at 0 and my particular time, 1200 seconds. So 0, and again, my particular time, 1200 seconds, minus my T infinity, which I'm given, over T initial, minus T infinity. And this is equal to C1. So I'll have a C1, and in fact, I'm going to go ahead and get those values. So in my table 5.1, so my C1 and my zeta 1. All right, so at 0.705, I end up getting, for my zeta, I've got 1.0935. And for my C1 value, I have 1.1558. All right, so with that being said, let's go ahead and just plug those numbers in, yeah? So I have C1, 1.1558 times my E to the negative, and it's zeta, 1.0935 squared, times our Fourier number, 0.1548. All right, so there's that guy. And then we are looking at, again, at the center. So yes, it's zeta 1 times r star, but again, that r star, because we're looking at r equals 0, r star is going to be 0. And so that means this whole value is just going to be 1. All right, and so I have one equation, one unknown, and so my temperature at r equals 0 and 1200 seconds, that ends up being 390. All right, perfect. Not degrees Celsius. Yeah, degrees Celsius. I'm going to flash back to the English units. Okay. So the next thing that we're looking at is Q over QL. You may recall that we have an equation sheet that sort of looks, or we have an equation on our equation sheet that almost looks like it's good enough. So I'm going to look at my equation sheet really quick. Not this one. There we go. So it's the one that's over here, this guy. So I'm going to copy that and put it right on my equation sheet, and then I'll see if I can like kind of manipulate them. So I have Q over Q naught. Remember that Q naught, it's the same thing as Q max. Okay, I'll call it Q naught, but again, it's Q max. I guess the reason that they use that Q naught is because that would be it's the maximum amount of heat transfer, but it would be when the center at R equals 0 comes into thermal equilibrium, because that's the last one, the last part or piece of the material that's going to come into thermal equilibrium with its environment. But this is equal to 1 minus, and then it's 2 theta star, and it's theta naught star, right? Over zeta 1. Come on. Okay. And then you'll see that you've got this other guy here. So he looks like a Bessel function, and he is. But he's just going to be, I'm going to read him off. You'll see it's the next row over, or the next column over, I'm sorry. So I'm inputting that guy. All right. So I know quite a few of these things. I know this because it's the same value as this. And I also know this because he's the same value as this. And although we didn't actually get a number for him, I will give you, I didn't write down a number. I do have one, right? This whole thing is that theta star naught, and we've got a value of 0.9605. So I've got all the stuff, and in fact, I can go ahead and get this guy. I'm going to write it in pink. I can get this guy as well. So if we're inputting 1.0935. Well, let's go look at our chart and see what that would give us. So I'm going to be looking at B4. You can see it's got a little subscript R instead, so we're going to be looking on that side. So So we're inputting 1.0935. So 1.09, so it's going to be between this guy and this guy. So I'm going to be looking between this guy and this guy. So I interpolate for a value of, let's see, yeah, 0.4689. So this one ends up being 0.4689. All right, so I have everything there. I'm almost there. This actually, all of this, by the way, this whole value right here is equal to, just so you know, we got a value. I've got 0.177. Perfect. Just to make sure that I and R subscripts are hand in hand for reading the charts. I and R subscripts are hand in hand for reading the charts. I guess you're asking about that guy, and L and R for. I don't know. I'm not really understanding. There's a little different subscript, and it's just a different equation. It's a different Bessel function.
I was just asking, like, you said that there's JR. Did you say that?
This one, it's just a different Bessel function. So if you look at table B4, it's just a different function. This function and this function, it's just different. So when you input something, you're going to get something different.
And so is that just J1?
Yes.
Okay, I thought that was an L and those went hand.
It's a number one, yeah.
Okay.
Yeah. Okay. All right, so we've got all that. I need to find Q over QL. So what I'm going to do, if I want to find Q over QL, I'm sorry, not QL, Q over L. If I want to find that Q per unit length, then I'm going to take that value, Q over Q naught, or Q max. Then I'm going to figure out a value for that Q max, multiply it. Okay, so now I just got Q, and now I'm going to divide by length. I'm going to put him right there. Okay, so I don't know what the length is, and that's okay. So let me get this guy now. All right. So this is, again, it's the maximum amount of heat that's transferred, and that would be for once this whole thing comes into thermal equilibrium with the environment. So what this would be is it would be mass times delta U, right? Remember, we did something very similar when we did the lumped capacitance method. We said, okay, well, this is, if I apply my first law of thermodynamics, Q minus W equals delta U plus delta kinetic energy plus delta potential energy. Everything would cancel out except the Q and the delta U. And if it's an incompressible substance, which is what we have, we can put this as MC delta T, right? Where the delta T that we're talking about is the delta T as this thing goes from an initial temperature of what was it? An initial temperature of 400 degrees to a final temperature of 400. I'm sorry, of 150. So this is MC theta initial, right? Again, that theta initial. This is T initial minus T infinity. And then you could put that mass in terms of rho times the volume, because I have rho, and then the volume, well, it's the volume of a cylinder, so it's going to be pi r squared, or r naught squared, times my length, and then I've got the c, and I've got the theta I, theta initial. So what you can see is that when I plug this Q naught here, when I plug that in, this guy right here, this whole guy right here, you could see that the L is going to cancel out, and I'm just going to be left with stuff that I know. I know R naught, I know rho that's given to me in the problem statement, and so what this is going to end up giving me, that's going to give me 16,000, 15, and it's actually kilojoules. It's a big number, kilojoules, and it's going to be per unit length, so per meter. And that's it. All right. Okay. So we'll go ahead and call it. Yeah. Same deal with the test. It'll be due Monday night. I will post tomorrow morning. I'll post the solutions for the check your understanding, a video of that, and it will be on the unit 3 playlist. Monday and Tuesday's lectures will be asynchronous. So I will post the video, but it will be just a video. And I will have yeah, Aiden, it'll be 5 conceptual questions and then 2 work it out problems. First one's probably going to be a numerical analysis, and then the other one is going to be transient conduction. So I will have office hours, but I'll probably move them to like 9 to 10, but I'll send out an announcement, and they'll be virtual so you can hop on. And if that doesn't work, if you do need to meet, you just shoot me an email. We can meet at another time. I'm happy to do that. You won't be able to see the chicken. Yeah, the chickens are not very smart animals, but
So for the exam,
yes.
The first problem is probably going to be like the one from Monday, and then the second one will be from the Tuesday through. Oh, sorry, that's my dog howling.
It's okay.
Tuesday through today, Thursday, right?
Yeah.
Okay, awesome. Thank you.
Can you scroll up to the problem statement? Yes. Okay.
And then after that, can I see the Heisler chart from the last problem?
Yes. All right, Josh, hopefully you've got it. So 5, 4, 3, 2, 1.
I got it.
Okay. All right, so let's go. Zoom in here. There we go. How's that?
That's good. Thank you.
Okay. So there was a question about when the exam 2 will be graded. If I look at what's there, it looks like that they're working their way through it. So hopefully soon. If it's not done by tomorrow afternoon, then I'll kind of ping them and see what's going on. Yeah. I agree. Other people should show their pets. I like pets. All right. All right. Well, you guys have a wonderful night. I'm going to put my timer on. If you have questions, just yell at me.
Question on the home.
Yeah.
It's just a conceptual one that
Mhm.
I didn't find anything that made sense to me on the equation sheet when I was looking at it. But the conceptual question was a cylinder and a sphere with the same diameter, thermal
Mhm.
properties, and external convection. It was just about whether for a sudden drop in ambient temperature, which center line temperature would decrease faster, I assume.
So think about which Q would be the fastest, or which Q would be the highest.
Q would be the highest.
Yeah.
Okay, so would I look?
So think
typically I
about
just
if you
look at
think
the
about it like just really generally, like if you took a snapshot in time and like you applied Newton's law of cooling, just say to the entire thing, it's dependent on the area, right?
Mhm.
And so your Q is going to be higher for a higher area. So just think about which one for a given diameter, which one's going to have a larger area. Yeah, yeah,
That makes sense.
yeah.
Thank you.
Mhm. All right, guys. I'll put my timer on. Thank you.